What are ANCOVA models? How to regress one quantitative variable and one dummy variable with two categories. You'd also learn the extension of ANCOVA model with combining one quantitative variable and one dummy variable with more than two categories or classes, and later combining with more than one dummy variable with interaction effects. We shall see various interaction effects between dummy variables as well as interaction effects between dummy variable and quantitative variable. Finally, application of dummy variable in seasonal analysis will be learned.
Continuing the thought process from the previous module on dummy variables and ANOVA models, a new understanding must have developed in your minds, bringing up new questions. So far, you have learned about what are dummy variables, how are they used, why are they used, and also about ANOVA models. This must have brought to your mind that can quantitative and qualitative both variables be used in a single regression model? Can there be interaction between them, etc.? All these questions must be bothering you. This module will help you to explain the concept of ANCOVA models, interaction between a qualitative and quantitative variables, and also explain the applicability of the same using various illustrations. Earlier, we talked about ANOVA models. Now, ANCOVA models are an improvement over them and are a bit more complex as well. Put in simple words, analysis of covariance or ANCOVA models are regression models which contain a combination of both qualitative and quantitative variables. These models provide a method of statistically controlling the effects of quantitative regressors called covariance or control variables, making them an extension of an ANOVA models. Further, using various illustrations, this module will also bring clarity to regression on one quantitative variable and one qualitative variable or dummy variable with two categories or classes, and regression on one quantitative variable and one dummy qualitative variable with more than two categories or classes. These illustrations will help you understand the fact that a single regression model may contain one quantitative variable and one qualitative variable with two categories or classes, or one quantitative variable and one qualitative variable with more than two categories or classes. This module also explains that there may exist interaction between dummy variables and quantitative explanatory in various combinations, such as between dummy variables or between dummy variables and quantitative variable. Various other intricate and interrelated concepts of differential slope coefficients, comparison of two regressions, and application of dummy variable in seasonal analysis is also discussed in detail in this module. On the whole, this module will clear all your notions regarding the details of dummy variables and assist you in using them with ease.
Analysis of covariance, that is ANCOVA, models are those regression models which contain a combination of both qualitative and quantitative variables. These models provide a method of statistically controlling the effects of quantitative regressors called covariates or control variables, making them an extension of the ANOVA models. Starting with our first topic, which will make you clear about how regression models with dummy variables may include both qualitative and quantitative variables as explanatory variables. We will at present focus only on dummy or qualitative variable with two categories to keep things simpler. Consider the following model. Yi is equal to beta 1 plus beta 2 di plus beta 3 xi plus mu I, where y is the dependent variable, beta 1 is intercept variable, beta 2 is differential intercept coefficient, beta 3 is slope variable, d is dummy variable, and mu is the error term. Here we have combined one qualitative variable di and one quantitative variable xi as explanatory variables. As stated above, when d takes a value of 0, it shows the absence of the attribute. On the other hand, when d takes the value 1, it shows the presence of the attribute. Also, it is important to note that the dependent variable is quantitative and error term satisfies all the assumptions of classical linear regression model. Consider the following example. Suppose that we take a group of 51 students in which we have 36 males and 15 females, and we collect data on their weight in pounds and height in inches. Now, taking weight as dependent variable and height as quantitative variable, we try to put a dummy variable for sex, in which sex dummy takes value 1 for male and 0 for female. Wi is equal to 122.9621 minus 23.8238 dumb sex I plus 3.7402 hi. The respective t values are minus 2.5884, 4.0149, and 5.1613. We find that dummy variable is statistically significant. That means there is a significant difference between the mean weight of two sexes, male and female, holding height constant. The regression results show that average height of males is greater than that of females, ceteris paribus. Average weight of males, where d is equal to 0, is approximately 122 pounds, and that for females is equal to 122.9621 minus 23.8238 into d equal to 1, that is approximately equal to 99 pound, holding height constant. Also, holding gender differences constant, the average weight goes up by approximately 3 pound on an increase in height by 1 inch. Mean height for females is equal to expected value of Wi given di is equal to 1 with hi being constant, equal to 122.9621 minus 23.8238 into 1 plus 3.7402 hi, which is equal to 99.1383 plus 3.7402 hi. Similarly, mean height for males is equal to expected value of Wi given Di is equal to 0, keeping Hi as constant, is equal to 122.9621 minus 23.8238 into 0 plus 3.7402 Hi is equal to 122.9621 plus 3.7402 Hi. Regression can include quantitative variables as well as qualitative variables with more than one categories. This is shown in the equation below. Yi is equal to beta 1 plus beta 2 d2i plus beta 3 d3i plus beta 4 xi plus mu I, where yi is equal to average annual salary of public school teachers in a state in dollars, xi is equal to spending on public school per pupil in dollars, d2 is equal to 1 if state is in the northeast or north central, is 0 otherwise. D3 is equal to 1 if the state is in the south, is 0 if otherwise. Here the base category is west. It is important to note that there are two qualitative variables and one quantitative variable x. Also remember, x is known as a covariate in case of the ANCOVA models. The results of the previous model are as below. Yi is equal to 13,269.11 minus 1673.514 d2i minus 1144.157 d3i plus 3.2889 xi. The standard errors are 1395.056, 801.1703, 861.1182 and 0.3176. The respective T ratios are 9.5115, which is significant, minus 2.0889, also significant, minus 1.3286, significant at 5%, and 10.3539, again significant. R square is equal to 0.7266. Star indicates p-values less than 5% and double star indicates p-values greater than 5%. The results suggest that keeping other things constant, a public school teacher's salary goes up by about $3.29 as public expenditure goes up by $1 on average. It can also be inferred that the differential intercept coefficient D2 is significant for the northeast and north central region, but not significant for the south, which is D3. To understand it better, consider the following example. Yi is equal to beta 1 plus beta 2 d2i plus beta 3 d3i plus beta 4 xi plus mu I, where y is equal to annual salary of a college teacher, x is equal to years of teaching experience, d2 is sex or gender dummy and is equal to 0 if male, is equal to 1 if female, d3 is the race dummy, is equal to 0 if white is equal to 1 if non-white. In the above equation, holding the years of teaching experience and race constant D2, the gender dummy, shows the differential effect of gender on annual salary of a college teacher. Similarly, holding the years of teaching experience and gender dummy constant D3, the race dummy, shows the differential effect of white and non-white on annual salary. Continuing with the same example, now we see how the interaction between two dummies can arise. Here, the two dummy variables, sex dummy and race dummy, interact with each other to have their joint effects on annual salary of a college teacher. Yi is equal to beta 1 plus beta 2 d2i plus beta 3 d3i plus beta 4 into d2i d3i plus beta 5 xi plus mu I. Here d2i into d3i gives the joint effect of two qualitative variables or dummy variables. Now mean annual salary of non-white female college teacher is given by expected value of yi given d2i is equal to 1, beta 3 d3i is equal to 1, keeping xi, and is equal to beta 1 plus beta 2 plus beta 3 plus beta 4 plus beta 5 xi. Here, beta 2 is the coefficient of sex or gender dummy and differential effect of being female. Beta 3 is the coefficient of race dummy and differential effect of being non-white. Beta 4 is the coefficient of interaction dummy and differential effect of being non-white female. Yi is equal to minus 0.2610 minus 2.3606 d2i minus 1.7327 d3i plus 2.1289 into d2i d3i plus 0.8028 xi. The t values are minus 0.2357, minus 5.4873, minus 2.1803, 1.7420, and 9.9095. R square is equal to 0.2032, N is equal to 528. P value below 5% are denoted by single star. Double star means P value about 8%, and 3 star means P value greater than 5%. Here we can see that on holding the years of teaching experience constant and adding all the dummy coefficients, we get minus 2.3606 minus 1.7327 plus 2.1289 is equal to minus 1.964. This figure indicates that the mean annual salary of a non-white female college teacher is lower by $1.96, which lies between the mean annual salary difference of male and female college teacher, which is $2.36, and the mean annual salary difference of white and non-white college teacher, that is $1.73. However, If we look at the statistical significance of the interaction dummy, then we find that it is not significant at 5% significance level. Thus, here in the above example, interaction dummy is not statistically significant, but it can modify the results of the two dummies if found significant. As you can see in the above image, there is an interesting interaction between a dummy variable showing marital status and a quantitative variable such as income, which together can have an effect on mean y. To further understand how such an interaction in the dummy variable and the quantitative variable takes place, consider the following model. Yi is equal to beta 1 plus beta 2 di plus beta 3 xi plus beta 4 d2i into xi plus mu I, where y again is the dependent variable, beta 2 is differential intercept coefficient, beta 4 is differential slope coefficient, d is dummy variable, mu is error term. Here d2i xi gives the joint effect of a dummy variable and quantitative variable. Here we can take the conditional expectation of the previous equation for dummy variable di to be 0, that means for the base category, and we get expected value of y1 given di equal to 0 and xi being constant equal to beta 1 plus beta 3 xi. Similarly, when we take the conditional expectation of the above equation for dummy variable with di equal to 1, we get expected value of y1 given di equal to 1 and xi being constant equal to beta 1 plus beta 2 plus beta 3 plus beta 4 xi. In the above equation, beta 2i is the differential intercept coefficient, which we are already familiar with, and beta 4 is the differential slope coefficient. Let us understand what differential slope coefficient is. A very crucial concept in dummy variables is differential slope coefficient. Beta 4, which is the differential slope coefficient, tells us by how much the slope coefficient of quantitative variable xi differs between two categories of dummy variable d. The example in the following slide will create further understanding on this concept. To illustrate it further, we consider an example. Yi is equal to beta 0 plus beta 1 xi plus beta 2 d2i plus beta 3 d3i plus beta 4 d2i into xi plus beta 5 into d3i xi plus mu I, where y is equal to annual earnings of MBA graduates, X is years of service, D2 is equal to 1 if Harvard MBA, is 0 if otherwise. D3 is equal to 1 if Wharton MBA, is 0 if otherwise. In this example, we expect each regression coefficient to be positive. In other words, annual earnings of MBA graduates is positively related to number of years of service as well as MBA done from whether Harvard University or Wharton University. Here beta 2 tells us by how much the average salary of a Harvard MBA differs from the base category, which is non-Harvard and non-Wharton. Similarly, beta 3 tells us by how much the average salary of a Wharton MBA differs from the base category, that is non-Harvard and non-Wharton. Now, when we take interaction between X, that is years of service, and the two dummy variables separately, then V in the model assumes that average starting salary as well as the progression of salary, which means the rate of change over years of service, is different among Harvard, Wharton, and other MBAs. This can be seen when we take the conditional expectation of the previous equation. For dummy variable, d2i is equal to 0 and d3i is equal to 0, we get expected value of yi given d2i equal to 0, d3i equal to 0, and xi is equal to beta 0 plus beta 1 xi. Similarly, when we take the conditional expectation of the above equation for dummy variable d2i equal to 1 and d3i equal to 1, we get expected value of yi given d2i equal to 1, d3i equal to 1, keeping xi constant, equal to beta 0 plus beta 2 plus beta 3 plus beta 1 plus beta 4 plus beta 5 into xi. In other words, in this example, beta 4 and beta 5 are differential slope coefficients. For instance, beta 4 tells us by how much the slope coefficient beta 1 of the quantitative variable xi, which is years of service, differs between the two categories of dummy variable d2i, which is whether MBA from Harvard or otherwise with ceteris paribus. There are four kinds of regression on the basis of statistical significance of differential intercept coefficient and differential slope coefficient. They are coincident regression, parallel regression, concurrent regression, and dissimilar regression. In the following slides, you will be familiar with all these types of regression one by one. We get coincident regression, as the name suggests, when the two regression equations coincide, which means there is no difference in differential intercept coefficient and differential slope coefficient. When the differential intercept coefficient is different for the two regressions, but the different slope coefficient is same, then we get parallel regressions. When the differential slope coefficient is different for the two regressions, but the differential intercept coefficient is same, then we find concurrent regressions. Finally, when both differential slope coefficients as well as differential intercept coefficient are different for the two regressions, then we come across dissimilar regressions. It is observed that in many economic time series based on quarterly or monthly data exhibit seasonal patterns, that is, regular oscillatory movements. Various examples could be sales of department stores, demand for air travel at Christmas and other major holiday times, demand for ice cream and soft drinks during summer, demand for money or cash balances by households at holiday times, or prices of crops right after harvesting season, etc. It is desirable often to remove the seasonal factor or component from a time series so that concentration can be brought to the other components such as the trend. Deseasonalization or seasonal adjustment is termed as the process of removing the seasonal component from a time series, and the time series thus obtained is called the deseasonalized or seasonally adjusted time series. For this purpose, dummy variables can be used to deseasonalize a time series. Let us consider an example which will provide a better and an in-depth understanding of how a dummy variable is useful in deseasonalization or seasonal adjustment. Sales T is equal to beta 1 plus beta 2 D2T plus beta 3 D3T plus beta 4 D4T plus mu T, where D2 is equal to 1 in the second quarter, 0 if otherwise, D3 is equal to 1 in the third quarter, 0 if otherwise, D4 is equal to 1 in the fourth quarter, 0 if otherwise. Note, first quarter is taken as base category to avoid dummy variable trap. Sales T is equal to 4767.750 plus 912.250 D2T plus 1398.750 D3T plus 2909.750 D4T. The respective T values are 14.714, 1.991, 3.052 and 6.350. R square is equal to 0.7790. From this regression result, we can conclude that the average sales in the first quarter were about rupees 4768 crores. In the second quarter, it was higher by about rupees 912 crores. In the third quarter, by about rupees 1399 crores, and in the fourth quarter, by about rupees 2910 crores. All these differences being statistically significant. The actual values of the intercepts in the various quarters can be obtained by adding the differential intercept dummies to the base quarter value. The individual intercept values are respectively all in crores. The first quarter Q1 equal to 4767.750. Second quarter Q2 is equal to 5680.00. Third quarter Q3 is equal to 6166.50, and the fourth quarter Q4 is equal to 7677.50. It is very important to note that dummy variables technique is an appropriate method of deseasonalizing a time series. We can deseasonalize the data by subtracting the dummy coefficient of each quarter from each quarter's sales figure. For instance, if we subtract from the sales figure for the fourth quarter of each year the number 2909.750, the resulting figure for that quarter will indicate the seasonally adjusted sales for that quarter. Regression may consist of both quantitative variable and dummy or qualitative variable. Such regression models are called ANCOVA models. ANCOVA models may consist regression of one quantitative variable and one dummy variable with two categories, or it can be extended to regression between one quantitative variable and one dummy variable with more than two categories. Also, more than one quantitative as well as qualitative variable can be incorporated in the regression model, which will produce some interaction effects. Such interaction may not be simply additive but multiplicative as well. It can be between dummy variables as well as it can be between dummy variable and quantitative variable. Then such an interaction between dummy variable and quantitative variable gives rise to a crucial concept of differential slope coefficient. Finally, we saw an important application of dummy variable in seasonal analysis.